Okay, folks, we are starting integrals today, which is very exciting. Integrals is essentially the third of AP Calculus. So we started by discussing limits, then we just wrapped up derivatives. Integrals is the last part of the course. Okay, so it's important that you have a good conceptual understanding of what we're doing before we start diving into some of the skills and the formulas that we're going to use in this unit. So we're going to return to sort of a classic example that we've used all throughout the course, which is speed and distance and time. Like I often do, I return to the example of riding a bike. And you can take a second to read the text here to talk about this situation. Right. So this is pretty easy to imagine. You've all probably ridden a bike or at least walk somewhere. So as you travel somewhere, your distance increases over time, right? Assuming you're going the same direction the entire time. And that's what we have here. And it says your speed varies over time, right? So you're not traveling at exactly the same rate, but your GPS is going to track that distance. So what we have here is we have time, we have distance, and we would assume that distance is some function of time, right? So your distance varies as time changes. Okay. Now, my question for you, and this is really a derivatives question, my question for you is how fast are we traveling over the first 3 hours? Okay, so that's a derivatives question, right? How fast are we traveling over the first 3 hours? Would be the change in distance over the change in time. So we can estimate that from the graph, right? Or we can take an average, really, from the table. So we could do 30 minus 0 over 3 minus 0. And that, of course, ends up being 10. Let's say our distance is in kilometers and our time is in hours, because 200 miles rather in 10.5 hours would be a little ridiculous. So let's say 10 kilometers per hour. Okay. Now we're going to do one more question here about this. And the question here is going to be, so here the question is, how fast are we traveling on the interval t from 3 to 5? Well, in that case, we do 100 minus 30 and 5 minus 3. So that ends up being 70 over 2, which ends up being 35 kilometers per hour. So, like I said, these are derivatives questions. So we already know from our work earlier in the year that we can calculate a rate of change given 2 points, or at least we can estimate it, right? So my speed may not be exactly the same this whole time, but we can make an estimate using the average. Okay. Now imagine I gave you something else, or imagine that your GPS rather captured different data. So here what I've done, right, is I've calculated the average speed for each of the following intervals, right? So that's every interval that was in the table before. Okay, so you can take a second, just take a look at the data. And as I said, you know how to do this for sure. We studied this much earlier in semester 1 and returned to it pretty recently too. I'm going to show you the graph of what all of these intervals would look like. Okay, so what I've done here is I've sketched the graph of the speed, right? So what we see, because these are all constants, is we have sort of a bunch of horizontal piecewise linear functions here. So remember our original function, we said d was f of t, so that was distance. My question for you now is, what should I label my vertical axis here? So horizontal axis is time, and then think of our derivatives notation here. Okay, so you could have said either d prime would make sense or f prime would make sense. Either works. So what we have here is a graph of speed based on our previous graph of distance, or our previous table of distance rather. Okay. So far so good, I think. This is all skills that you've already had. Now let's build towards our understanding of the integral here. Okay. So let's say I gave you this to begin with. So I gave you just the average speed. Let's say that we didn't have any of these calculations here. So we just had that. My question for you is, how could we figure out what the total distance would be for the first 3 hours? So I know I'm going 10 miles per hour for 3 hours, or 10 kilometers per hour rather. So you guys know that that ends up being distance times time, right? Or sorry, rate times time gives you 30 kilometers, right? And that's what we had in the original table. Let's say I wanted to find now the distance we traveled in the first 5 hours. Well, I'm going to do the same thing as I did before, so I'm going to do 10 times 3 for the first 3 hours, right? Plus, so that's my first interval in the table, or the first little piece segment of my graph here, plus 35, so that's speed for the second interval, times 5 minus 3 is 2 hours. Okay. So this would be the total distance traveled, so that's 30 plus 70 is 100. Okay, and notice, and that's 100 kilometers at 5 hours. Notice if I go back up to my original table, that's what we had, right? Now the last question, here's the really important question, is how do these things show up in the graph? So take a second to think about that. If you get this right now, I'm going to be impressed. Okay, so what I've done here is I've altered the graph to make this a little bit easier to see. Okay, so notice if I fill in the area underneath my graph, what we get is some rectangles, right? And my first rectangle, let's take a look at it. My first rectangle has height 10 and width 3. So if I wanted to find the area of that rectangle, 3 times 10 is 30. Same math we did here, right? My second rectangle, well, it has width 2 and height 35 based on my graph, so this would be 35 up here. 2 times 35 gives it an area of 70. So that number down here. 30 plus 70 is 100. So that's the distance we traveled in the first 100 kilometers. So the answer to my question, how do we connect these numbers that we use to find distance from speed to the graph, is it's the area underneath the graph. Okay. And that's an integral. I'm going to ask one more question before we move on. And the question here is, what would I do using my graph to find the total distance traveled? Total distance traveled, how would I do that? Okay. What you should have said is add the area of all 4 rectangles. And you can check if you want what that would get us. They would add up to 200, which is the total distance we started with from the graph. Okay. So the goal here is to see the connection between my graph of speed, in this case it's kind of a bar graph, right? My graph of speed and distance. Remember, this graph is a derivative, right, of distance, right? The area under that derivative gives me my original function. Okay. So take a second to take that in. And then I'm gonna summarize this for you. Okay, key takeaways, capture these in your notes. We're going to develop these throughout this entire unit. So for now, just capture them. So first key takeaway is that if we have a graph of speed or velocity, to find the total distance traveled, that's represented as the area beneath the graph. So here is our graph from before, right? This was a graph of speed. The area of these rectangles represented distance. Okay. This is the opposite, and by opposite we mean inverse operation, just like addition and subtraction. That's the opposite of finding a derivative, right? So this is the first integral we're studying here, is the area underneath this rectangle. Okay. The reason that this is all useful is that it allows us to analyze situations where we only know about the rate of change. Okay. So if we're only given speed, this allows us to figure out where we are at a specific time. The last thing we're going to talk about is notation. So notation is super important because this is how we communicate about these things. So here is our first example of integral notation. So as a reminder, f of t in this case represented distance. F prime of t represented, we'll say speed. We're traveling the same direction, so speed and velocity are kind of interchangeable in this case. F prime of t was speed. Okay. Now, what we would say here to write this down, integral notation, this is brand new. Draw this kind of tall, skinny S guy. This is the integral sign. And we'd say the integral of f prime of t dt equals f of t. So this is called an indefinite integral because it's just talking about the general function. In this case, remember we analyzed the total distance traveled. So here we could also say the integral of f prime of t dt equals, and remember if we go all the way back up, we know we traveled 200 miles total, equals 200. But we have to talk about specific times. So we traveled 200 miles in the time from 0 to 10.5 hours. So this is what integral notation looks like. The way you read this is as the integral of f prime of t with respect to t. So this dt tells me that t is the variable that I'm interested in. Here, we'd read this as the integral from 0 to 10.5 of f prime of t with respect to t is equal to 200. So if you're in a spot where you can, read those out loud to yourself a couple of times, just like I did. When you're ready, we're going to practice some very basic examples in the next lesson.